All right, so this lesson is on geologic time and how we can put a date on rocks. How do we actually know how long ago something happened? Well, there's really two different ways that we can determine how long ago something happened. We can put a relative age on it, or we can, like it says there, we can use relative dating. Relative dating is actually pretty simple. You're just determining the order of past events, but you don't have to know any specific dates. For example, if let's say I'm just really fuzzy when it comes to American history, and I don't know any of the specific dates that things happened. But if you were to give me a list of events, let's say on that list there was the Revolutionary War and the Civil War and World War One and uh, COVID happening. Those are all events that have happened in American history. And even if I don't know any dates, I could say, well, first the Revolutionary War happened. Don't know when, but I know that that was the first thing that happened. And then later on, the Civil War happened, and then I know World War One was the next thing that happened out of the events that we're talking about, of course. And then later on, COVID happened. That was the most recent thing. And even though I don't know any specific dates, I can say first, second, third, and fourth, and that's good enough for relative dating. You're just saying oldest or youngest or anywhere in between. The other way of aging something or putting a date on something is finding the absolute age. Now, with the absolute age, you are determining with a specific number the age of past events. When I say exact, I don't mean like down to the second necessarily, but if you know event A happened 2.2 million years ago, event B happened 1.9 million years ago. It's more than just saying oldest, second oldest, third oldest. You're actually assigning a number that goes with it because we have a good idea of when event A happened. Like I said, it doesn't have to be, down to the exact year. Scientists, for example, say that dinosaurs went extinct like 67 million years ago. We don't know if it was March 2nd or November 3rd or, the specific year. But we do know that it happened 67 million years ago. And so that is an absolute age. Okay. Long time ago, if you were a humble English peasant like this gentleman and you saw a rock that looked like that, you would probably be amazed and confused because you would have no idea how rocks could look like that or what events caused them to look like that. And you would hope that to solve your confusion, someone would come along and make sense of the madness. In the 1600s, there was a guy named Nicholas Steno who not only did he wear sweet hats, but he also came up with the four principles of geology. And those principles, they're often referred to as Steno's principles. They're still in use today, and they help us find the relative ages of rocks. So here's a statue of him in Europe, I'm assuming. Here's his first principle. Principle number one, superposition. So we're already pretty familiar with this principle from past units, but it basically says the oldest layers are on bottom and the youngest layers are on top. Think about it. If you were going to add another layer of dirt to the pile, it would go on the very top, and the ones that have been there the longest are going to be on the bottom. So superposition is rule number one or principle number one. Basically, we go back to our laundry basket analogy. You put clothes in on Monday, they're going to be at the bottom. You add some on Tuesday, they're going to go on top of that. On Wednesday and Thursday, and so on and so forth. So if you just walked in and saw this laundry basket, you could probably guess that you saw the blue or that you wore the blue clothes first. At least you threw them away first because of where they are in the basket. If we apply this to rocks, we know this one is the oldest, this one happened next, and this one is the youngest out of A, B, and C. Of course, the very youngest would be right here on the top. Principle number two, the principle of original horizontality. This seems like a long, fancy word, but honestly, it's pretty simple. The principle of original horizontality essentially states that when rocks are originally created, when they're first formed, when these layers are first formed, they're always in parallel horizontal layers. They're not tipped like this. They're not folded and squiggled like this. They haven't been hit by earthquakes yet, as shown here. Originally, they're always formed horizontal and flat. Later on, different events can happen, like tectonic plates can collide and the rocks can get tilted. They can fold together, they can be hit by an earthquake. Later on, events can cause them to not be horizontal, but they always start out horizontally. Regardless of what they look like now, they started out horizontal. It's going to look something like this. When these layers are originally created, they look like that. They're happy because they're following the rules. And then later on, let's say another continent smashes into them, and now they're not horizontal. Now they're tilted or they're slanted, but they weren't formed like that. Okay, principle number 3. This one basically is stating that what is over here is also over there. The name of it is the principle of lateral continuity. Lateral means side to side, and continuity is the same as continuous. So if I were to dig down beneath my feet 10 feet and I find a layer of red clay, it would make sense that if I walked 30 feet to the left and dug down 10 feet, I could find that same layer of red clay because that layer is continuing in all directions. So if you're inside a canyon hiking with a buddy, and over on this side of the canyon, you're like, you'll never guess what I see. I see this gray layer of charcoal. And then they're like, yeah, oops, going the wrong way. Your buddy's like, I bet I can guess what you're seeing because that layer continues over onto my side. Okay, principle number 4. This one's probably the most complex, which is why we saved it for last, but it's also, in my opinion, the most useful for our test. So, cross-cutting relationships, pop quiz. If you walked into the kitchen and you see this scenario, you got a cake with a knife sticking out of it, what do you assume came first, or which entered into that position first? Was the cake sitting on the table and then the knife put in later, or was the knife floating above the table and someone came along and was like, oh, since that knife is floating conveniently above the table, I'll just slide the cake into it. Of course, the cake had to be set down first before you could place the knife in it. This principle is the principle of cross-cutting relationships. The thing that gets cut, in this case, it's the cake. The thing that gets cut is always older than the thing that cuts it. So with rocks, you can have igneous intrusions, which means you have basically liquid igneous magma that is forcing its way up through the cracks and basically cutting across that layer. And when you see a sedimentary layer that's been cut by, and I'm doing air quotes with my fingers right now, an igneous knife or an igneous intrusion, you know that the layer of sedimentary rock had to be there before the intrusion happened. The cake is older than the knife. All right, so here's what it looks like in rocks. Instead of inserting a knife from the top, like I said, these igneous intrusions leak up from the bottom. So let's walk through this step by step. This layer is going to be the oldest because the principle of superposition tells us that the oldest thing is going to be on the bottom. But how do we know it wasn't this part of the bottom or this part of the bottom? Well, since these layers are cutting across this horizontal layer, we know that they are like the knives, and this layer, this horizontal one, is like the cake. And the cake has to be older. Now let's move up one level. How do we know this level is the second oldest? Well, again, it's being cut by this knife, and it's being cut by this knife, which means it is older than the things that cut it, and it's definitely older than the thing above it. So this one has to be the second oldest. Next, we have this knife cutting right here. But how did I know this knife is older than this horizontal layer of rock and older than this one? Well, when this lava leaks up and makes it to the surface, it's not going to build up any higher on its own because it's still liquid at this point. If it does leak up across the top, it's going to form probably a little bulge here or even leak out horizontally, like we see up here actually. But because this is basically sheared off right at the edge of the layer, we assume that anything above here was exposed to the surface, and as erosion happened right across this surface, wind and water, it got eroded away, so now it's just flat with the edge of this layer. Because it's underneath this layer that's titled Eocene sedimentary rocks, we know that since it's beneath it and it doesn't cut it, that this one has to be older. So at one point we had layers 1, 2, and 3, and then this horizontal stripe layer existed. And we know this one has to be older because it is cut by this knife. Our next layer is this knife as it slices through. Then we have this leaking from some unknown volcano over here off our screen. Piled on top of that is more Oligocene sedimentary rocks, this grayish layer right here. I guess they're all gray, but this flat gray one right here. And that's it. That takes us through all those layers. Again, it seems a little complicated, but if you follow two principles, two rules, which one is lower and which one is doing the cutting, you'll be in good shape. Does this type of thing ever happen in real life, though? Or am I just making up complicated situations just to annoy you? Well, it does happen. So here we have 4 different layers of rock. One of the layers is this lower red layer. Another one is this kind of orangish brownish layer on top. And then we have another one you can barely see poking out of into the screen right here. We also have an igneous intrusion that's acting like a knife coming out of the ground, going up to the top of this red layer. So let's walk through it. Which one's first? Well, we know that the lower layers are always older, but here we have 2 layers, the black one and the red one, that are both touching the bottom. So between the cake, which is this red layer, and the knife that's cutting it, we can always assume that the cake is older, meaning the knife would happen second. On top of that, we have layer 3, and then finally we have layer 4. Back to the laundry basket. This next part is about fossils, and specifically index fossils. So if you were to see someone else's laundry basket and it looked like that, even without seeing what they were wearing on those particular days, you could assume that they wore the blue one first and then the red one, and so on and so forth. You could tell the relative age of these layers, but you couldn't tell me the absolute age. You couldn't tell me whether this one happened a day ago, an hour ago, or a month ago, just by looking at the piles. You'd hope it would be just a day ago, not a month ago, but who knows. In order to get an absolute age, we need a little bit more information. What if you were digging through this laundry basket because you're nosy and for some reason you're going through this person's laundry, and inside the red layer, you happen to find 2 special Halloween socks. And you know that this friend of yours only wears these Halloween socks 1 day a year on Halloween night. Would that give you enough information to tell how old this red layer is? Hopefully it would. If you only wore those those Halloween socks on Halloween, you can assume that the red layer surrounding them was also something you wore on Halloween. And everything above that would be more recent, and everything below that would be older than Halloween. These socks are kind of like an index fossil. An index fossil gives us a way of putting an age on the rocks surrounding them, because a fossil is going to be the same age as the rocks that they die in, roughly. So there's 2 rules for becoming an index fossil. There's many, many types of fossils, but only a few of them are actually called index fossils. Number 1, they've got to be widely distributed, because let's say that there's a specific fossil that's only found around Utah Lake. Would that fossil be any use for identifying the age of rocks down in St. George or in Kansas? No, because that fossil is only found around Utah Lake, so it could only help identify the rocks around Utah Lake. A good index fossil is widely distributed. So, for example, a fossil that is found everywhere in the western United States would make a better index fossil than one that was just found around Utah Lake. Rule number 2, they only live in a short time period. This is kind of like the sock example we were using. If you wore those Halloween socks every day of the year, then finding them rolled up in the red layer of clothes wouldn't really mean much. It could be Halloween, or it could be Christmas, or it could be, February 10th. It could, if you wear the socks every day, they don't necessarily tie the red layer back to Halloween because the socks aren't directly tied to Halloween anymore. But if you only wear the socks one day a year, that actually gives us a good timestamp on when you wore those clothes. That's similar to an index fossil. A good index fossil is only found in a short time period, and it's a specific time period. So it might be, obviously it's going to be more than a day because species tend to live for millions of years. But for example, if we find a particular fern fossil that we know lived between 100 and 120 million years ago, even though that's a 20 million year time period, it still can tie that layer of rock out of the billions of years of Earth's history. We can specifically tie that layer of rock to a 20 million year period, which is actually pretty specific when it comes to rocks. If you found that fossil at, 500 million years ago and 200 and 100 million years ago, and also, you know, let's say it's even still alive today, then when you find it, it's not really going to give you a specific time for when that rock existed because you don't know exactly when the plant existed. All right, if you were to look at a bunch of different outcrops, and an outcrop is basically a location, so you could label this one Riverton, Utah, you could label this one St. George, and this one New Mexico, and this one Canada. Doesn't matter. But as you dig down in these outcrops, you're going to find different rock layers, okay, different ages. The deeper you go, the older it's going to be. As you find these different fossils, you need to classify, do they follow both rules? So let's take a look. This fan-shaped shell thingy, is it widely distributed? Can you find it in every location? Well, it's definitely in location 1 or outcrop 1, definitely in number 2, definitely in number 3, and oh look, it's actually found in layer 4 or outcrop 4 as well. So far so good. It matches the rule for being found in many locations. Now let's see if it's only found in one particular time period. Here in outcrop 1, we see it in this first layer, but we also see it in this third layer. So it's found across multiple time layers. And in outcrop 2, my goodness, it's found in literally every single layer. So it is not found in only a specific time period, and it's not going to be a good index fossil. If you had this imaginary outcrop 5, and you're like, I wonder how old these rocks are, and you found one of these fan-shaped shell things, it wouldn't tell you whether you were in layer 1 or layer 2 or layer 3 or layer 4. It wouldn't be able to nail down a specific time period because it's found everywhere and any time period. The correct answer that matches both these rules is this trilobite fossil. See how it's found in every single outcrop, but only in the second time period. Now, if you had this imaginary outcrop 5 over here, say you're working in California, and you're digging and you come across a trilobite, you know exactly which time period you're working in because that's the only time period you find it in. It's a good index fossil. And the rest of these, they're just fossils. All right, unconformities. You can get pretty complex with unconformities, but here's what I hope that you know. An unconformity is the name that geologists give a gap in the time record. So imagine a record is being, like a history book is being recorded, and it started, let's say, 1,000 years ago, okay? And someone's been keeping this record every year of all the big historical events that happen in each year for the last 1,000 years. And someone comes along while the scribe is getting a drink or something and rips out 100 years worth of history. Say they rip out, uh, the 1900s. Okay, you go straight from 1899 to the year 2000, and then the scribe comes back and just continues writing with today's news. That would be an unconformity. That huge gap in the record. The event still happened. We just don't have any record of it anymore. So as you're reading that book, you'd go straight from, the trek westward and a westward expansion and all that, all the things that are happening in the late 1800s. And then you'd turn the page and you'd be like, the internet? What the heck? I just missed 100 years of history. What happened? Well, an unconformity happened. In geology, an unconformity doesn't happen by a mischievous, book hater. It happens because of erosion. Rocks are the history books of the world. And if you erase those rocks through erosion, you're getting rid of the history they recorded. So let's look at a few different ways that can happen. As these rocks are recording history, let's say part of the history is they get squished by a mountain. That's going to add some heat, time, and pressure to those rocks. And if the mountain is then eroded away, leaving just those metamorphic rocks exposed, you'll know, okay, something made those metamorphic, but I don't know what it was. It must have been a mountain range sitting on top of them that no longer exists. And so when you see these young sedimentary rocks being deposited on top that aren't squished and they're also much younger, you know that the unconformity happened somewhere right in here. This line right here represents probably 100 million years of events that happened that have been erased. No one ever saw that mountain range, but we know what it did. We see the aftermath. It's kind of like coming across footprints in the snow, and even though you don't see the person who left them, you still see the footprints. This is a common one. You see an angular unconformity. Basically, these rocks are deposited, and then something comes along that tips them. Maybe another continent crashes into them. As they get tipped, that is a process that's probably taking tens of millions of years. It's a slow tip. But then the tipping stops. Okay? There's no more collision with the other continent or whatever was causing it. Well, now when new layers are deposited, because of original horizontality, they're going to be horizontal. When you see this line right here, I've got it highlighted in green, but when you see this boundary between angled layers and horizontal layers, you can recognize it probably took tens of millions of years of time just to tip those. And the only way we know that is because now we see tipped rocks right next to horizontal rocks. So the gap in time is represented by that boundary. This is probably my favorite one. You slowly build rocks over tens of millions of years, layers of rock. And then one day, water is like, yeah, but erosion likes to take these away. So we just erase those pages right out of the history books. Then, when new layers are created, kind of like the newest chapter being written in a book, it is much, much older, and you see a huge gap between these rock layers. That is your unconformity right there. Okay, that's all I've got for you for this assignment. Let me know if you've got any questions. I'd love to study with you, and good luck on the test.